All right, guys, hopefully you can see the slideshow. I don't have anyone in here right now. Someone might jump in, but I'm going to use this as our recording. Oh, shoot. Okay, so give me 1 second. Let me shut the door. All right, if you hear weird talking, I have online kindergarten going on at a desk in my room right now, so they're working on letter sounds. So if you hear talking in the background, I'm really sorry. I'm trying to teach kindergarten and you guys, and that's why I'm a little befuddled today. But we're going to talk about just some quick topics that I know I've had assignments for you guys about, and you might be confused on. So I've made a little PowerPoint using some of the textbooks information, and I also have some visual concepts to show you, and I'll explain it. Remember that there are questions throughout this video, so if you're watching this not live, you have to answer those questions in order to get your points for this lecture. So don't forget that. And other than that, if you have questions, ask me later. Okay? So the first thing you should see on your screen, hopefully, is atomic radii. So atomic radii is just like a radii that you learned about in geometry. A radius is half of a circle. So from the center point of a circle to the outside, that's a radius. Okay? Sorry, these letter sounds are distracting me going on in the background. So from the center, or what the center of an atom, from the nucleus to the outside of the electron cloud, that's our atomic radii. Okay? So you'll see it says boundaries of an atom are fuzzy. There is no hard line that says this is the end of an atom. That's because our electrons are a cloud. Okay? Electrons move all over, we know that. So there's no hard line. Clouds don't have hard lines. So if you're going to compare two atomic radii, you have to measure them in the same conditions, same temperature, same pressure. All of that has to be the same. Otherwise, you're going to befuzzle that fuzzy line and make it even worse. Okay? And then the definition we just talked about is 1/2 of the distance between the nuclei. So from the center to one side. Okay, that's half. If you went from one side to one side, that would be whole. But we want the center to the end, just like a circle. Hey, get up and watch kindergarten. Okay? Let's see how to do this. All right, so what does that have to do with the periodic table? As you move to the right, so if you're moving across the periodic table, let me get mine. So here's my periodic table. Okay, I could probably open one online, but it would confuse me to open another tab. All right, so as you move to the right, so as you're starting here, and this might be left to you, I don't know if it's a mirror, but as you move this way on the periodic table, I can't figure out which is your right, which is your left. Okay, yeah, I was right. All right, sorry. So as you move to the right on the periodic table, the atoms tend to get smaller, okay, across a period. So remember, across a row, okay? The trend to smaller atoms across a period is caused by the increasing positive charge of the nucleus. So the bigger the nucleus, so the more protons, remember, atomic number tells us our number of protons, and as we move to the right, our atomic numbers get bigger. So the more protons, the more positive charge you have attracting those electrons. That should make sense. More positive is going to attract more negative. That makes the atomic radii smaller. So if your protons are all here in the middle and your electrons are here, if you get a whole bunch of protons, they're going to pull on the electrons more and pull them in. Does that make sense? If you only have one electron, or one proton, I'm sorry, then this electron is just going to go wherever it wants. There's not much pulling it in. Okay? Now, as you go down a group, so as you go down the periodic table, okay, atoms tend to get bigger. They have more electrons. They have more protons, but they also have more electrons. Since we know the rules that electron orbitals can only hold 2 electrons on the first ring, 8 on the next ring, and so on and so forth, then if an atom is going to get more electrons, it has to have more rings to put them on. More rings makes a bigger circle. Okay? Hopefully that makes sense. That one's a little bit of just Oh, duh, that makes sense. Common sense. So hopefully it sticks. If you have questions, ask me. Here is a picture of the periodic table showing you what atomic radius is doing. Okay, so this top one right here, the blue one, that's atomic radius. The darker the shade of blue, the bigger the atomic radius. So as you go down, the atoms are getting bigger. As you move over, you'll see it kind of lightens up. It might get darker in random spots, but for the most part, the trend is it's getting smaller as you move to the right. The next box, this chart right here, we're not really talking about this yet, but I thought it was nice to throw it in. We're going to move into bonding and ions and your radii when you take electrons away. So we'll come back to this one at a later date. I just left it on there so you can see it. So that's it for atomic radii. Very basic. It's just the distance from the nucleus to one edge of an electron cloud. They get bigger as you go down, smaller as you move to the right. Okay? The next thing we're going to talk about is ionization energy. An ion is the beginning of ionization. An ion is when you take an electron away from an atom or you add an electron to an atom, giving it a charge. Okay? So electrons have a negative charge. So if you take an electron away, that atom is now positive. It has more protons than electrons. All right, the example right here is sodium. If you take away a sodium, so if sodium loses an electron, now it has one less electron than a proton, which gives it a positive charge. Okay? The process that takes away electrons or gives an electron is called ionization. Okay? So making something positive or negative is called ionization. And the energy that is required to take that electron away is the ionization energy. Okay? So if that proton, that nucleus full of protons is holding on to this electron out here, you're going to have to put some energy in to pull that electron away. That energy is the ionization energy. Okay? It's like if you were holding on to a $10 bill and your brother was trying to steal it from you. You're going to have to put up a fight. They're going to have to come and get it and use some energy to take it away from you, because otherwise you're not going to give it up. Okay? All right, so according to in reference to the periodic table, ionization energies of the main group of elements, so that excludes this chunk in the middle, transition metals, okay? There we go. So in general, ionization energies increase as you go. So increase as you go right to left. It takes more energy to take electrons off over here than it does over here. Okay, hydrogen's going to give that thing up like crazy. Lithium, beryllium, they're all going to give them up. Oxygen, fluorine, and whatnot, they're not going to. Okay, so this is harder, higher ionization energies, lower ionization energies. And then as you go down, it actually gets easier to give one up. So at the top, it's a little bit harder than down at the bottom. Okay? And this is because the bigger the atom, remember we talked about as you move down, the atomic radii gets bigger. So if you have a really big atom, and here's your nucleus, and your electron's way out here, it's not going to have as much force pulling it in, so it's going to be easier to pick off. Okay? So the bigger the atom, so as you move down the periodic table, atoms get bigger, their ionization energy goes down. It's easier to pull electrons off. As you move across the periodic table, it gets a little bit harder to pull an electron off. Okay? And ionization energy is just the energy it takes to take an electron away, to give it a charge. Okay? So that's it for ionization energy. Here's a picture, I forgot I put this on here, that shows, so the periods of the periodic table, so period 2, 3, 4, these are the rows, remember row 2, row 3, 4, 5, 6, and 7. You can see that at the beginning of the periods, so down here at the bottom, the ionization energy is down here, oops, shoot, sorry. And then as you go across, all the way from lithium to neon, ionization energy goes up. But as you go each period, so as you go down each row, the ionization energy is lower. Okay, so that just backs up what we just said. All right, valence electrons. We got 2 more topics to get through. Valence electrons are the electrons on the outside of an atom. We did a little bit with these before Christmas, and I think you guys did really good just knowing that you count the rows, and that's the number of valence electrons. It goes up to 8. Okay, you can only have up to 8. So chemical compounds, when they form bonds, they bond with electrons. They bond with the electrons on the outside ring. Those are the valence electrons. Okay? So the electrons that are available to be lost, gained, or shared, so the electrons on the outside that can be given up, that can orbitals where we can take in electrons, or some elements even share those electrons on the outside, those are all valence electrons. Okay? They're on the outside, none of the middle, all the way on the outside ring, valence electrons. All right, I got a little thing to show you. I don't know if it'll work. We might have to open another tab. Let's see. Give me 1 second to figure out how to do this. Okay. Okay, I think you can see it. I'm going to keep going like we can. Hopefully we can. Hopefully you'll be able to hear it too. We'll see. Here we go. All right, let's see if we can get back to the thing. Oh, look, I did it. Okay, now let's see if we can get the slideshow back up. So, in case you missed it, didn't understand or something. Why is it now making it like full screen? Okay, whatever. I liked it better the other way, but this will work, right? Okay, so in case you missed it, valence electrons are the electrons around the outside. Noble gases, so the group that is all the way over here, I don't know what you guys can see, so I'm hoping you can see this. This group right here, the noble gases, they do not have any reactive electrons. So their valence electrons do not react. That's because they already have 8. Okay, if you remember me talking before Christmas, the magic number of 8. Everything wants 8 on the outside. So we're going to move into bonding and how elements come together to bond with each other and their valence electrons. And the reason they bond is so that they can get 8 on the outside. Okay? And that little video also showed you, if you forgot, that excluding transition metals, you can count valence electrons. So row 1 has 1, row 2 has 2. Skip the transition metals. This is row 13. Take off the 1, it has 3. 14 has 4. 15 has 5. 16 has 6. 17, 7. And 18, 8. Okay? The only exception, and the one that threw you guys off, is helium. Helium lives in row 18, and your first instinct is to say it has 8 valence electrons, but helium only has an atomic number of 2. So it only can have 2 electrons. Okay, so helium's the only exception to the rule. All right, I hope that made sense. I hope you can see what I think you can see. I don't know, but that's it for valence electrons. We have one more thing to talk about, electronegativity. All right, I think that you guys can see this slide. Again, I hope you can. Otherwise, I'm going to watch this video, and it's going to be a big waste of my time. Okay? But electronegativity, so valence electrons, so the electrons on the outside, they hold atoms together. So they are what holds hands with another atom. Water, we all know it's hydrogen and 2 oxygens. I'm sorry, 2 hydrogens and 1 oxygen, H2O. Okay? The electrons from hydrogen and oxygen are holding hands. That's how we make water. They're bonding together. If they let go, we now have oxygen gas, hydrogen gas, and we've made a bond. Okay? So they hold hands, they stay together. Valence electrons hold atoms together. Okay? So in many compounds, the negative charge of the valence electrons is more concentrated in one than another. Okay? So that means that when they're holding hands, one atom, either the oxygen or the hydrogen, is going to be pulling those electrons and pulling that negative charge more than the other one. In our example of oxygen and hydrogen, oxygen is really pulling those electrons. Hydrogen doesn't really want them. Okay? So oxygen has a higher electronegativity. It's pulling the electrons from hydrogen. Okay? Electronegativity is the measure of the ability of an atom in a chemical compound, remember compound means more than one, so oxygen and hydrogen, to attract electrons from the other atom. So hydrogen has 1 electron, oxygen has 6. Oxygen really, really wants 8. Hydrogen wants 2, but it doesn't really care. It comes together and oxygen grabs the electrons and pulls. Oxygen has a higher electronegativity. Okay? And it's really easy to know who has a higher electronegativity because electronegativities tend to increase as you move across the periodic table. Let me grab my periodic table. So as you move across the periodic table, your electronegativity increases. Okay? And then as you move down a group, they decrease. Okay? Or in some groups, so it says they decrease or remain about the same. They do. I'm gonna just remember they decrease because really they don't change by much. You're gonna get a periodic table that has no other numbers on it except for the electronegativities of an atom. So you're gonna be able to see how they stay the same or decrease. But I don't think we're gonna do that until maybe I get you guys back because that might trip you up a little bit. But as you move across the periodic table, so as you're going from hydrogen across, then your electronegativity is increasing a lot. As you move down, it's decreasing a little bit. Okay? I think that was our last thing, so I have a little video to show you. Again, I don't know if it's going to work. Let's see. Oh, it's okay. All right, hopefully you can hear this. Here we go. Excellent job, Levi. Excellent job. Another important bubble connects to the picture. All right. So what this is telling you is as you move from the right side, so the hydrogen side of the table, all the way over, the electronegativity goes up. Fluorine is the most electronegative with an electronegativity of 4. That's the highest we can get. And as you move down a group, you can see that they start a little bit lower and they end a little bit lower. All right? So let's see if we can get back here. So that's all I have for you. This is all your assignment today is just a lecture. And if you're watching this live, you're good and golden. If you're not, then you need to answer the questions throughout this video. Hopefully you've been answering them because hopefully I've been able to put them in there. If you have any questions, let me know. Next week, you will be starting assignments with valence electrons, electronegativity, ionization energy. So I really need you to understand it. I'm posting these videos online. If you need to go back and watch it later, whatever you need to let me know, okay? Last semester, a lot of you dug yourself a hole and you pulled out with D's because you were barely surviving. Don't be dumb. Don't do that again. Put a little bit of effort in and we'll all be fine. All right. Have a great, what day is it? Tuesday, and I will see you guys on Thursday. maybe.
Okay, one more question, boys and girls. One more, well, actually, we're going to finish the story.
I don't know how to do this. So right now you're just gonna look at me for a second.
And draw.